In this video, we will look at the concepts of decomposition, pattern recognition, and abstraction. When writing code to generate some kind of 3D model, we can think of it at two levels. At the lower level, we are writing code that calls geometric functions. In this example, we might write code to generate a series of polylines. We then loft those polylines to create polygons. And finally we replace each polygon with two tubes. However, it is also possible to think about your code at a higher level. We can apply semantic concepts such as decomposition, pattern recognition, and abstraction. Let's look at how this might be done. Decomposition breaks down a complex problem into smaller, more manageable parts. When applied to spatial modeling, these parts can be procedures that generate some part of the model. These procedures can be defined using semantic constructs related to the model being generated. In this case, we might define procedures to make arcs, make panels, and make diagrid. Pattern recognition looks for similarities among problems or processes. If such patterns are found, then they can be solved using a common code. In this case, we can see that although each panel is different, there is a simple pattern to creating the diagrid. By replacing each panel with two diagonal struts, a diagrid structure will be created. Abstraction focuses on the important spatial information only, and ignores irrelevant detail. First, we can define the level of detail required in our model. In this case, we decide that we want to ignore the detailed modeling of the joints between the struts. Instead, we want to model the start point and end point of each strut, as well as the strut diameter. We can then abstract the process of creating the diagonal struts into a function. We can create a user-defined function where the input parameter is one panel, and the return value is a pair of struts. Within the body of the function, we can ignore the neighboring panels and the neighboring struts. We can also give the function and its parameters semantic names related to the modeling task. And we implement the function in a way that has semantic coherence. For example, the struts are generated with a structural logic, where the diameter is proportional to the length. When we are thinking about breaking down a complex program into procedures and functions, cohesion is a key concept. Cohesion refers to the degree to which the elements inside a procedure or function belong together. In general, you want your procedures and functions to have high cohesion. This means that the procedure or function has few links with other procedures or functions. The procedures or functions in your program can then be described as being loosely coupled. This means that when you change one part, the impact on other parts will be minimized. We often find that high cohesion aligns well with procedures and functions defined with clear semantics. For spatial information, one strategy that can help is skeletal modeling. With skeletal modeling, a highly simplified skeleton is defined. Such a skeleton captures the minimal spatial information required for generating all the other parts of the model. In the example, the skeleton consists of a minimal set of polylines. The different parts are then all generated from the skeleton. But there is no interaction between the parts. So changing the way that one part is generated will not affect any other part. This strategy creates a loosely coupled set of procedures with high cohesion. Each part also has clear and well-defined semantics.